So you want to learn about Laplace transforms? I think I've got you. Just listen to me.
Kennedy, why are you acting like you're in a 1980s techno-cop movie again?
I'm sure you're wondering, what the hell is a Laplace transform? I wondered the same just a couple weeks ago. So let me give some backstory. The Laplace transform is named after Pierre-Simon Laplace, a French mathematician who lived during the 18th and 19th centuries. He was born to a cider trader and lived a comfortable life because of his father's business. His parents expected him to become involved with the Catholic Church, so at the age of 16 he enrolled in a university's theology program. However, while at this university, he realized his love for mathematics, and his professors saw great scientific potential in him. Once he realized how badly he wanted to study math, he dropped out of college and moved to Paris. After a while, he became a professor at École Militaire and began pumping out math papers like it was nobody's business. Throughout his mathematical career, Laplace began to work on ways to transform differential equations so that they'd become easier to solve. In 1809, he developed what we widely consider the Laplace transform. So what exactly is the Laplace transform? In short, the Laplace transform is a way to change a function into a different function that will make solving ordinary differential equations easier. That doesn't really say much about what it actually means though, does it? Essentially, taking the Laplace transform of a differential equation is sort of like pushing that differential equation into a complex, unreal realm. Laplace transforms are really nice in that you're able to take an ordinary differential equation, which uses calculus, take the Laplace transform of that, and get an equation which you can use algebra to find the solution for. Now, as you know, it's a lot easier to use algebra to find the solution of an equation rather than calculus. Let's pretend that we have an equation of time f of t. We can convert this into a function of the Laplace variable s so that we end up with the capital F of s function. This f of s function is the Laplace transform of f of t. So it sort of looks like this, with the cursive L indicating that a Laplace transform has been taken. Okay, I suppose I should step back and actually give a definition as to what the Laplace transform is. We can define the Laplace transform as the capital F of s is equal to the integral of 0 from the left to infinity of f of t times e to the negative st dt. Of course, applying this function to every single equation that needs to be Laplace transformed can be quite tedious. Thus, a table has been developed to make it much easier. On the left of the table, you can see the original functions before being Laplaced, and on the right is their Laplace transform counterparts. Of course, once you have the Laplace counterpart, you can now solve it using algebraic methods. However, you also have to use the inverse Laplace in order to take it back to the real dimension, so that you may actually use the results in any application you want. Things also get trickier when you start discussing Dirac delta and Heaviside functions. Dirac delta functions are used to model an impulse of something, whereas Heaviside functions are used to model a step up to a certain level of something. You might be wondering, what are the real-world applications of the Laplace transform? Well, there are many ways it's used. First off, in modeling electric circuits, or deciding how much medication needs to be prescribed over time. Maybe just modeling something with depreciation, again over time, and really so much more. It is difficult to learn how to use the Laplace transform in mathematics. After all, it's not necessarily easy to figure out something so abstract. If I had been able to know the Laplace transform before actually learning about the Laplace transform, I would remind myself that it's not just some esoteric, inapplicable topic. So many real-world situations with differential equations, especially in engineering, use the Laplace transform. And the Laplace transform is there to make my life easier, not worse. In actual class, I would tell myself to not get frustrated. Working with quote-unquote imaginary things is challenging, but it's important to continue to press on through and try to fully understand what's going on. And it's not necessarily super-duper necessary to understand each intricacy behind the theory behind Laplace transforms. That's graduate-level math. Don't feel bad. And I would need to remember that the Laplace transform is literally just taking a function which would need calculus to be solved and making it so that it can be solved with algebra. Embrace the Laplace transform. Don't hate it. Lastly, if I had to watch out for some things before learning the Laplace transform, I would remind myself to learn the difference between Heaviside functions and Dirac delta functions. They're similar but almost opposite, kinda, but not really. Just understand the distinctions between the two, but also know that their similarities can be helpful in understanding them. Keep up on my notes, watch my algebra errors, and most importantly, don't overcomplicate things.
Wow, Kennedy, you do know your Laplace transform. But you're still not a robot. Stop acting like one.